have Max from the economics department, who is going to talk about data and decisions. I could say many great things about Max. I've seen him present many times, and it's super clear. The one thing that I chose to say is that being an applied person, there are so many times that I encounter a problem that say, oh, the econometric solution must be so easy. Why is that there is not a single econometric paper solving this for me? And Max is one of those exceptions to this problem. He's going to talk about why randomizing is the wrong way to go. I think that
among other things.
very interesting work.
Well, thanks a lot for the introduction and for organizing this. So what I'm going to try to do today is kind of give a quick overview of like a decision theoretic perspective on issues of method in econometrics in particular, but in empirical research more generally, which I think is kind of a nice complement to what we've seen before, which was about causality. And so kind of to get started, so when you consume empirical research, you run into all kinds of methodological problems, and here I'm giving you a kind of random selection. So for instance, suppose you're in a setting where the data actually don't identify the policy effect you're interested in. Are those data still useful? Can you still make decisions about policies or rank different policies? Another one would be, suppose you're running an experiment and you observe a bunch of covariates before you're running the experiment. How should you use them? And should you randomize? Why should you randomize? Or what else could you do? Yet another setting, suppose you want to pick some policies, say a tax rate or class sizes in schools, or whether to assign some medical treatment to people who suffer from a particular disease. And you have some data. How do you use the data in an optimal way if you have a finite amount of data? And one more, so I guess something that many of you will be familiar with. There's been this huge growth in various algorithms proposed in the machine learning literature. And a lot of them seem to do pretty well, but how can we think systematically which one of those we should choose in a particular setting? And how do we evaluate the performance of such one of these procedures? And so the claim that I want
to... Could you speak up a little bit, or maybe move closer to the center of the room?
Yeah. So the claim that I want to push today is that many questions such as these essentially reduce to math problems once you have properly specified your problem. So once you've explicitly stated all the components that need to be stated in order to solve such a problem. And there's a bunch of key questions that you should answer, I think, in most settings. I mean, the first one seems kind of obvious: what are the available data? But it's basically what kind of data sources do you have at your disposition and do you want to use? Then the second one, which can be quite a bit trickier, is what's actually the space of feasible actions or policies that you're interested in. And so I want you to think about actions in a very general sense. So this could be like picking an estimate, so like a number of what's your best guess of some true effect, say. It could be a 0-1 decision, is some theory true or wrong. It could be picking a tax rate or a class size or an amount of redistribution or social insurance or any number of things. And so being clear what the set of actions from which you can actually choose is really important. Then third, what are the unknown states of the world that matter for your problem? So state of the world here is basically anything out there that you don't know and which you care about in the context of your problem. So this could be, for instance, say you decide whether or not to advocate a particular medical treatment, and the unknown state of the world could be what's the average effect of that treatment on patient health. Or if you're interested in picking a tax rate, then you might be interested in how much does the tax base react when you change the tax rate. Or say if you're interested in a theoretical question, then the unknown state of the world might be whether some hypothesis is actually true or not true. Okay. Then fourth, how do we evaluate an action for a given state of the world? So that's basically saying what's our objective function? What's the goal at the end of the day that we want to achieve? Suppose you knew the true state of the world and you pick some action, how do you evaluate that? So say in the medical context, you might be interested in maximizing average patient health, for instance. Or in the hypothesis testing problem, you might be interested in not making a wrong decision. And you might care differently about rejecting a theory that's true or not rejecting a theory that's wrong. And so that's kind of part of 4 here. How do we evaluate actions? 5th, how do the data relate to the state of the world? So the reason we care about data is because they tell us something about this underlying state that we need to know in order to make decisions. So that's what's usually subsumed in a statistical model, is relating underlying states of the world to a distribution of the data that we observe. And finally, we have to take some stance on how we deal with uncertainty. So after you've observed the data, you might know more about the state of the world, but you still don't know what it is. And so there's this remaining uncertainty that there's various ways of dealing with that I will get to more precisely in a minute. And yeah, you have to take a stance there.
So in computer science, we're very comfortable with writing down a problem as a math problem, and then we just solve it and not really worry about how it relates to the world all the time. But in economics, is this framework you're setting out, is this always like comfortably accepted, where you say, okay, we're just going to write this as a math problem and then solve it?
It's I think on some level the interesting part is actually in answering these questions. Once you've answered them, you give them to some mathematician or
do you evaluate?
So what's kind of funny, I think, in economics is, I think this type of thinking comes very naturally to economists, but for some reason not to econometricians. So I guess part of my research is trying to push perspectives like this, and in order to push people to think more systematically about what they're actually doing when they're dealing with data and what the goal at the end of the day is. Of course, there's all kinds, there's also a lot of craft or art involved in setting this up in a way that you can solve in a neat way and where you understand what's going on. But I think the big thing is kind of having plausible answers to these questions and being explicit about them. Okay, yeah, so here are a bunch of examples from my research that basically correspond to the questions I put up in the first slide that are roughly motivated by an approach like this. And I'm going to talk a little bit more about the second one and the last one. So the second one is about experiments and why you shouldn't randomize. And the last one is about the risk of machine learning, which is about evaluating machine learning procedures. And here's the overview of the rest of the talk. So I'm first going to give you a brief review of statistical decision theory, so kind of the textbook version. And then I'm going to apply this framework to these 2 settings. So I'm going to take the framework of statistical decision theory, and I'm going to argue that it implies that you shouldn't randomize. This includes experimentation. And then very briefly, I will talk how we can think about the performance of procedures such as lasso or rich or pretesting, and give some geometric intuition for the behavior of such procedures and under what conditions which one of them will perform better. Okay. So here's my kind of 1-slide summary of statistical decision theory. And this picture basically corresponds to the 6 questions I just put up here. So the different items in this picture correspond to these questions. And let me go through them in turn. So there's some underlying state of the world, which I denote theta here. So this is everything that kind of matters for the problem at hand, which you don't know, and which in some sense we assume exists out there. And this underlying state of the world very importantly, has 2 different roles in this framework. The first role is it relates to the data. So the distribution of the data depends on what the true underlying state of the world is. That's why the data are interesting to begin with, because that's why they tell us something about this underlying state of the world. And so how they are related, that's determined by the statistical model that we're considering. So I'm writing it here as a density, probability density of the data x given the underlying state of the world theta. And so we have some observed data x, and they have a probability distribution which depends on theta. And then there's a second role of the theta, which is it matters for our decision at the end of the day. So we're going to evaluate our decision, and we're going to evaluate it in a different way depending on what the true theta is. So for instance, you could think that you might want to estimate some causal effect. Then the theta would include the true causal effect, and then this evaluation could involve the distance between your estimate and what the true effect is. And you're doing worse the further you're away. Or this could involve, say, if you're testing a theory, you get a loss if you don't get it right. So if you reject the theory and the theory is true, you get a loss, or the other way around, you get a loss too. If you get it right, you don't get a loss. Or say if your goal is to maximize patient health, then the loss might be how many patients are dying, or something like that. And these are going to depend on your action A. So this might be, for instance, whether you prescribe a medical treatment or not, and they are going to depend on the true effect of the medical treatment. And then next component is the policy space. So what are the decisions we can actually make? So this might be, for instance, a set of medical treatments that we're considering, or the set of objects we're estimating, or whatever it is. And so we think of these actions as being a function of the data that we observe, right? So we are picking an action A, and that action A is related to the data X through some decision function delta. And kind of the problem of decision theory is coming up is a good delta at the end of the day. So the other things are the components that are given by the framework once we've answered these 6 questions. And then the goal is to pick a delta that performs in some sense well in terms of this framework. And so the decision function delta maps the data X into a decision A. And then at the end of the day, we get loss, or if you want to flip the sign like economists, then you can call it utility. And that depends on the state of the world and your decision A. Any questions about this framework? So I'm going to use this for the rest of the talk.
So you're also coming up with a statistical model, right?
Yeah, so that's something that we're kind of assuming to begin with. So this could be a very general thing that's just saying, whatever, there's some probability distribution of the axis, and then the theta might be the average of that probability distribution or something like that. So this doesn't have to be parametric, is what I'm saying. But we have to somehow relate the distribution of the data to the object that we care about. Otherwise, the data are useless.
Would you say that like machine learning basically assumes the same model?
Yeah, there's nothing special about machine learning as far as I'm concerned.
This is a general model that both economics and machine learning are using.
I mean, I don't know how many people are thinking in terms of this framework, but I think it's very natural to think in terms of this framework. So I'll get back to machine learning later and put it in this framework, at least some approaches. Yeah. Okay. So.
But I guess in machine learning, the arrow on the top would often be called a learning algorithm rather than a decision function, and the square in the northeast corner might be called a hypothesis H rather than a decision A.
Sure, there's all kinds of different terminology that people are using. Yeah. Yeah.
I think it's basically the same.
It's syntactically the same, but the emphasis is different, because here you're thinking of this decision as like a policy, whereas in machine learning you're just like pick the way that you understand the world,
and then you make the decision.
Like check whether you're understanding the world well.
I mean, as far as, to the extent that I know machine learning, the way I think about it there, usually this is some kind of prediction, say, you're predicting some outcome given some other stuff that you observe, or I guess that would be supervised learning, or.
So in this case, do we just assume the statistical model as something given a priori, and then we are focusing on like choosing the best like decision function?
Yeah. So basically, that's something that's part of these 6 questions, right? How do the data relate to the underlying state of the world? So this involves assumptions. So for instance, the setting that we've seen before, if you have a randomized experiment, then that's an assumption about how the data relate to the state of the world, and then you can get some average causal effect, for instance, by comparing two means for the 2 treatment arms. So any kind of assumptions on how the data are generated enter here the statistical model. Okay, so what I'm saying is spend a lot of time thinking about the components of this, set this up properly. Once you've done that, then we can go kind of to the generic framework of decision theory. And the first step there is to calculate what's called the risk function. So the risk function is expected loss given the true state of the world. So it's fixing one theta, so fixing one true state of the world. And given that theta, there is some distribution of the data x that's determined by the statistical model. We plug that into a decision function delta that gives us a distribution of our chosen actions. And then we evaluate it based on the loss function, which depends on theta and the decision function. So the theta enters in 2 ways here. It determines the distribution of x, and it enters the loss function. And what this is giving us is basically an evaluation of the performance of a particular decision function for a given state of the world theta. Right? And just to reiterate, our goal at the end of the day is picking a good delta. We don't know what theta is. And I guess so the way I would think about how this complements a lot of machine learning is that people come up with all kinds of delta that might be pretty smart or complicated or whatever. It's not always clear how we think about the performance of these. Okay, so risk function, expected loss of a decision function delta. It's a function of the true state of the world theta, and so that's a problem. So for instance, if I tell you what the true causal effect theta is, say, then your best estimate of that is just going to be that number, right? So that you could never beat that. But that's going to be a pretty bad estimate if the causal effect is far away. So what this is saying is that this gives you a ranking of deltas, but that ranking depends on the thetas. And so the key, in some sense, the central problem of this statistical decision theory is that you have to make this trade-off across different states of the world. A procedure might perform well for some states of the world and poorly for the other. And there's no way you can get around this trade-off in some sense. And there's different ways of dealing with this trade-off. One is the Bayesian approach, where you essentially assign weights to different states of the world. How much you care about one value of theta versus another value of theta. And these weights are usually called a prior or a prior distribution. And once you pick such a prior pi, then you can integrate out the risk function or average the risk function across states of the world, and it's giving you what's called base risk. And now that's a number. And that number you can now use to rank decision procedures. And then in principle, you can just pick the delta, which is giving you the smallest base risk. Another approach, which in some sense you can think of as being the very pessimistic approach, is looking at the worst case. So for any given delta, suppose you're facing an evil nature. Evil nature is always picking the worst possible state of the world for your given choice of delta. And then you get the worst case risk or supremum of risk or maximum risk, which is denoted by R bar here. And that's again a number. And then you could pick the delta which minimizes this number. So that's ensuring you against the worst case. Yeah, so I mean, there's a lot to be said about this framework. I'm going to leave it at that.
I don't know if you were going to walk us through a simple example, but if you had to relate this back to Emily's talk a second ago, I've got observational data on health outcomes. What would those criteria say about what kind of estimate I would use?
So let's go through the health outcome example. Say the state of the world is the true relationship between diet and your mortality, say. Then you have a data set, say an RD data set like that relates your body mass index to the recommendation made by the doctor and ultimately to the diet that you actually adopt. And so you have this data that's kind of part of the statistical model. Then the decision function is you observe this data. It might be like a scientific problem where it's just getting a good guess of or good estimate of what this number is. It might be a policy problem, which is should public policy recommend particular diet, say. So those are different possible policy spaces here. You map the data that you have into a decision there, and then your loss might be, for instance, the average mortality, but maybe corrected for some cost of public health interventions.
So for the Bayesian risk, so it does require that I know the distribution pi over theta, right?
So
that seems to be a lot of information to require.
So the key is that this is not something you can know, right? There is nothing to be known. The pi is a trade-off you have to make. There's no true pi, right? There is just some theta out there in the world, and
your frequentist or Bayesian.
Yeah, sure. Maybe we can get into a lot of debates here. The point I want to make here is so you have this risk function. If you accept the framework from the previous slide, then the risk function tells you how to rank procedures for a given theta. It doesn't tell you how to rank procedures globally. And then there's no way you get around this trade-off across different theta. You have to make this trade-off somehow if you make a decision. And there's actually formal results that anything admissible, so anything that's not uniformly dominated, so anything where there's no other procedure that has a risk function that's lower, whatever the true theta is, there is some prior that corresponds to that. So in some sense, I mean, there's some formal caveats to that, but basically what that tells you is that from the perspective of decision theory, everything that makes sense is a Bayesian decision procedure at the end of the day. But yeah, I guess that's bringing us away a bit here from where I want to go. But the basic framework is clear. And so what I'm going to do for the rest of the talk is I'm going to apply this basic framework to the two settings that I mentioned, to randomized experiments and to some machine learning procedures and how to evaluate them. Okay, so here's the claim via experiment I should not randomize. So it's a claim I've gotten a lot of pushback for. So what I want to do is I want you to think about experimental design as a decision problem. And so what's the typical setting when you run an experiment, for instance, in an economics context, but also maybe in a medical context or a sociological context or maybe also in a private sector type context? You have some set of experimental units. And for these experimental units, you know some stuff. For instance, you know how old they are, what gender they are, things like that. And you might potentially use this information of these what's called baseline covariates at the point when you decide to assign them to a treatment. So maybe you might assign them to recommend, to stay with the example, recommend a high-fat diet or not a low-fat diet, or not recommend that. And when you do this assignment, you might use the data from the baseline covariates. You might also use potentially a randomization device U. So U might be you just throw a coin or a dice or whatever. And so you map the decision function is mapping the baseline information and the randomization device into an assignment of everybody in your sample into a treatment, low-fat diet or not. And different objectives you could think about here. One possible one is getting a precise estimate of the causal effect of interest. And so now for the ease of exposition, I'm going to assume that your randomization device only takes on a finite number of values. So U takes on one of the values 1 through U bar. And it's completely random, so it's statistically independent of everything else. Okay? And then I'm going to introduce some notation here, which might seem useless at first, but it's going to be useful. So I'm going to write delta U. This is a deterministic decision function which only depends on the x's. And corresponds to the decision function delta of x and u that we would get if you took on the value little u. Okay? So the delta of xu is a randomized decision function. Delta u is a deterministic decision function that you get if you just fix the randomization device at the value little u. And when we have that notation, what we can do is we can look at the risk function again, right? So this is just repeating basically the last slide, only that we have u in here now. So this is the average of the loss given the state of the world for our given decision function delta. And given that u is independent of everything else, this is basically the law of iterated expectations. We can write this risk function as a weighted average of the risk functions for the delta u's. Right, so this is just writing this expectation where we make explicit the randomization over u.
So in your example where my loss function was like, there's some true theta of the world and I just want to learn theta, and my loss is the difference between what I estimate. I don't quite see how it can fit into the syntax.
So in that case, the most common loss would be the squared error. So here we might have that this is the difference between our estimate at the end of the day and the true effect, then the square of that, which is often usefully decomposed into a variance and the squared bias. And then what this is saying is that the mean squared error of our randomized procedure is a weighted average of the mean squared errors of the deterministic procedures for the different values of u. Okay. So this is giving us the risk function as a convex combination of the risk functions for the delta u's. And now the risk function gives us only a ranking for a given theta. If we want to pick in some sense, globally optimal delta, we have to do one of the ways of aggregating this to some global number. So if we do base risk, we take the risk function and integrate it out over a distribution of thetas over the prior. And basically, just by linearity, everything is going through. And we get that the base risk of the randomized procedure is equal to a weighted average of the base risk of the non-randomized procedures. And again, the same thing for a minimax or for the worst case risk. So the worst case risk of delta is just the weighted average of the worst case risk of the delta u's. And
sorry. Can you back up to slide 8? I don't understand the. Okay, so now forward to slide 9. I don't understand the justification for the last equation on the slide. If let's say that theta is let's say the theta takes the value Saturday and Sunday.
Sure.
And that I have a procedure which does well on Saturdays and poorly on Sundays, and another one which does well on Sundays and poorly on Saturdays.
Yep.
And then I have the weighted average of the two procedures where I toss a fair coin, that's my U, and choose one or the other procedure according to the coin toss outcome. Then I'll have something that does kind of well on Saturdays and kind of well on Sundays and never too poorly on either day. So
So
to me, when I take a maximization over theta.
So the key is kind of the sequence of steps here. Okay. So I think your argument is one that people sometimes make, which I don't find super convincing, but which would violate this, which is basically saying, suppose there are two games that you can imagine you playing against the evil nature here, right? So one is the game you pick delta, then you randomize, basically you pick the decision, then nature moves and screws you over. That's this one. Another one is you pick delta, then nature moves, then you pick u. So u is a way for you to trick out nature because you're picking the number after nature moved. In that case, this would be violated. But so basically, which is kind of a funny logic, because then once I tell you what your random number is going to be, suddenly you cannot use this random number anymore. But I guess let's maybe talk about this later. For the base risk, there's no ambiguity here. So if we stick to the base risk, what this is basically telling you, right? So we have that the base risk of the randomized procedure is a convex combination of the base risk of the deterministic procedures, and that immediately implies that this weighted average has to be larger than the minimum. And if the minimum is unique, then it's strictly larger. And so that's saying any randomized procedure has to be weakly worse than some deterministic procedure. So if you just want to pick an optimal procedure, you're always fine by just doing the non-randomized ones. And on top of that, you're going to be strictly better than really randomized ones if the non-randomized one is unique, that's optimal. So here, if we go back to the experimental setting, when do we get this uniqueness? So if you have no covariates, right, everybody in your sample looks the same, then it's not unique. Then it doesn't really matter who goes into the treatment group and who goes in the control group, because they're all the same anyway. In that case, this becomes just an equality, and then it doesn't really matter, and you might as well randomize. However, if they all look different, so people have different ages and incomes and education and gender and whatever, and so at the end of the day, no two people look the same, then this generically becomes unique, and then the non-randomized one is going to be strictly better than the randomized one. Just reiterating, allowing for randomization never improves risk and usually makes things worse. And that's precisely the reason when we estimate or test, we don't randomize, right? Nobody would propose adding random noise to your estimator, And so it's kind of funny that they do propose adding random noise to your treatment assignment.
Is there a relationship between this and doing numerical integration? So there is a case, for example, if you want to integrate something multiplied by something that is distributed, like expectation of a function, where a random term is distributed normal, and you know that instead of randomly drawing from the normal distribution, computing and taking average of that, it is better to like basically fix some numbers and like integrate.
That's exactly, yeah. I've never thought about that connection, but it's exactly true.
But there are also cases in which when you do numerical integration, picking this type of risk can go very wrong. Is there cases where this could go wrong for?
I mean, so that's kind of a tricky question in terms of what you condition on when you say going wrong. So basically, that comes back to how what we are averaging over when we're defining this risk function.
Yeah.
And so when in the paper I'm more careful, I define it kind of conditioning on the covariates that we observe, but averaging over a sampling procedure for the unobserved potential outcomes. And then this cannot go very wrong. If you condition on the unobserved potential outcomes, which I don't think you should, but then in principle you can construct examples where things can go wrong.
Ask a question about so in the model that you introduced at the very beginning, at the time I thought it makes perfect sense to think about that model, but now I don't really understand how I should think about unobservables in that model. Right, this one.
So I mean, I guess you could think of them as the part of theta. Yeah. Or the theta might be a distribution of the unobservables, depending how you want to think about it. But
then how should or it's just that result is so counterintuitive to me. So how should I relate what you said that we shouldn't do randomization with the standard procedure of saying that like randomization is good for controlling the unobservables? Like what's the,
so
I
basically,
think I'm missing something there.
I mean, so here I just told you why you shouldn't randomize, but not what you should do instead. And basically what you should do instead part gets to that. And essentially the intuition is to get causal effects, you want to compare apples with apples and oranges with oranges. And so by making your treatment and control groups as similar as possible in terms of stuff that you observe, you're also making them as similar as possible in terms of stuff you don't observe, at least in expectation. And so in some sense, when you have a large sample, then this is just going to be the same as randomizing. When the law of large numbers kicks in, they're just going to look the same. In small samples, you just by chance might get them to look very different. So you run a medical experiment and all the old people are in one group, all the young people are in the other group. Then you have a problem, and the optimal procedure avoids that by making them look as similar as possible.
So I understand the argument for the sort of stratification, but why does balance and observables imply balance and unobservables?
In expectation, because whatever, if they're dependent, right, then making them more similar, then it's going to, on average, make them more similar in terms of unobservables.
Can I just follow up on that quickly? Isn't the fundamental problem that we can't balance on all observables? Namely,
yeah, so I mean that's again what you should do part in the paper.
No, I meant at a deeper level, which is there's one observable which we cannot balance on, which is treatment. So in some sense, I totally buy the argument that if we could balance on all the observables by construction, but in a way, I thought a lot of the tension of even the issues of are we, yes, we balance on a bunch. Like the most extreme example is I find two people, the twins, and now they're even twins, are genetically the same. One of them goes to college and one of them doesn't. And the more you get balanced, you're like, the more you might be picking up on the unobservable of motivation.
Oh, but you're still in a setting where the experimenter assigns the treatment, right? So.
Oh, I see. That's the point. So treatment.
It's just the treatment is assigned non-randomly, but it's assigned by the experiment. There's no self-selection here.
I see.
Oh, I see.
So you've got experimental control sitting in the background the whole time.
So another way of saying that is it's a CT, but not an RCT.
Good. That makes sense.
Yeah, just so I understand, is this similar to I do an RCT, but my variances were crazy, so I try to fit a model afterwards to balance out some of that? Is this like a similar logic for it?
Yeah, so basically, in some sense, what this is going to do is almost allowing you to avoid that. So right, if you could make them exactly the same, then it doesn't matter what you control for afterwards. But the motivation for, if you hadn't done this, for then running a more complicated model with control for stuff is exactly the same.
strange way to think of randomization, though, because in many cases, you fix the data and then you do a randomization test. Where here, you just marginalize over everything. So it's a very different way of how you think about randomization.
So randomization tests are not part of the decision theoretic framework. There's no way to justify a randomization test in a decision theoretic context.
That's the point of the randomization experiment, though, that you can condition the data and do a randomization test and have some exact...
But you can't condition on the treatment, right? So, which is what we usually do when we do name and Pearson inference.
You can condition on output.
But you cannot condition on treatment, right? So the different approaches to inference are distinguished by what you're conditioning on. Neither of them is consistent with a decision theoretic perspective. So there's no way of rationalizing randomization inference a la Fisher in a decision framework. But again, maybe we can talk afterwards about this. So, I want to talk just briefly about the second part of. How long do I have? I don't know what.
Randomize your answer.
Okay. I'll just give you quickly a brief intuition. So, risk of machine learning, presenting here kind of a very stylized setting, but which captures a lot of what I think is going on in various. It's called different in various contexts, but you can think of as supervised learning. So, setting is we have a bunch of dimensions i equal 1 to n. For each of them we observe xi. And we want to estimate the expectation of xi, which I denote mu I here. So you should think of this not so much as the raw data, but maybe as some useful transformation. So maybe the xi might be coefficients of some regression or something like that. And our goal is to estimate the mu I, so maybe the true regression coefficients. And we have estimators mu I hat, which are functions of the data, and our loss is, say, just squared error, so the difference between the average difference between our mu I hats and the mu I's. Okay, and so there are two key features of many machine learning procedures, which are regularization and data-driven choice of tuning parameters. And so in the paper corresponding to this part of the talk, we talk a lot about both of these. Here I'm going to talk a little bit about regularization and how to do regularization well. There's a bunch of canonical examples for such regularized procedures. So our component-wise estimators, so basically the mu I hat is a function of xi and possibly some tuning parameter lambda. And one example would be Rich, which comes out actually of a Bayesian approach when you do a normal prior and normal model and take the posterior expectation, which is basically a linear shrinkage of the x towards 0 in this case. All kinds of versions you could do of that. Second one is Lasso. So Rich corresponds to a quadratic penalty. Lasso corresponds to an absolute value penalty, or L1 penalty, which yields a mapping from x to mu I hat, which takes the form that it's basically constant equals 0 in an interval around 0 and then takes off is 45 degrees. And yet another one might be pretesting, where you say mu is 0 if your x is in the neighborhood of 0, and otherwise you just take x. So in terms of a picture, these would be functions that correspond to these different ways of doing regularization. So Rich is just giving you a line with a slope of less than 1. So depending on how much you penalize, you get a different slope here. Lasso is giving you this solid line here. So that's flat around 0 and then takes off. And the width of this interval, again, is the regularization parameter. Pretesting also flat around 0, but then jumps away to the 45-degree line.
Does this picture assume that all of my covariates are orthogonal?
So there are no covariates here, right?
Just one.
So we have a bunch of xi's, but I'm assuming that we have these component-wise estimators. So I guess, yeah, if you're thinking of the regression setting, then this would correspond to if you had orthogonal regressors, and the xi's would be the OLS coefficients.
Oh, I think I misunderstood what the x-axis was. Never mind.
Yeah. Okay. But this is the mapping from xi to mu I hat. And now, and in principle, you could come up with many other different ones here, and people have to some extent. And so the question is, which one of those should we pick? Should we pick Lasso? Should we pick Rich? Should we pick pretesting? Should we do any of these, or maybe just do OLS? And I want to just give you one neat little result that speaks to that. Again, the paper, there's a whole bunch more. So one way to think about that is assume you have your set of xi's and you draw a random index capital I. So I is just uniformly picking one of the little i's. And then for each of the i's we have the observed xi, which has some distribution pi, right? So that distribution might be different for every I actually. But it has an expectation of mu I by definition. Okay? So this is kind of the randomness that just comes from the data. This is a useful construction that I'm going to leverage in a second, where we just pick randomly one of the i's. And if you do this random picking, then what we can define conceptually, even if we don't know what it is, we can define a conditional expectation of mu I given xi. Because once we are randomizing over the components I, the mu's are random, and it's kind of like a prior, but except it's not a prior, it's just a sample distribution. And for that kind of pseudo prior, we can calculate the posterior expectation m star of, sorry, this should be x actually, not y. The posterior expectation m star of mu I given xi. And now the neat little theorem tells us if we want to think about the mean squared error of any such component-wise estimation procedures, such as lasso-rich pretesting and so on, this has some irreducible component v star. So that's just the conditional variance of the mu I given the xi's for this construction. And then another component which does depend on the estimator that we're picking. And it depends in a very particular way on it. Because the second part, that's just the L2 distance between the estimation function that we picked and this construction m star. So if we had an estimation function that was equal to m star, then we would be golden. That's the lowest mean squared error you could achieve here. If you don't, then your mean squared error is just the L2 distance between the function you picked and the optimal one. So any given data generating process is going to map into an m star, and then in some sense you want an estimation procedure that reproduces the shape of this m star as well as possible. And actually it turns out if your dimension n is large, then you could even consistently estimate the m star. And if you have some data-driven choice of the tuning parameter, and here I'm assuming the oracle optimal one, which turns out you can consistently estimate too, then basically you end up with a projection in L2 space. So you're going to have that the risk of your procedure, say lasso, is equal to the closest you can get within the space of these kinked functions to the optimal function m star. And you can think about how any true data generating process which corresponds to the distribution of mu i's, how that corresponds to the m star, and for instance how this intuition of sparsity, that there are a number of true zeros, would map into some shape of what the m star would be and so on. And so that's part of what we do in that paper. And I guess I'll stop here.
I'm curious if you or anyone else have thought about generalization of your framework to cases where there's more than one loss function. So an example that I'm picturing is that a researcher is doing a study. The researcher's loss function might be 1 if the paper gets rejected from a top journal and 0 otherwise, whereas society's loss function has something to do with whether the results give useful policy insights. And you would somehow want to know whether there's a decision procedure that does well simultaneously with respect to both loss functions, because that's the condition under which research can lead to society.
I mean, then you're very much in the realm of economics and game theory and mechanism design, which is how you could align the incentives that people would actually do something like that. If you're like just thinking of, I'm a researcher and I want to do both, then I guess in some sense you have to face a trade-off between different objectives, which is very similar to the trade-off between different theta, right? You could think that at the end of the day you're going to maximize some type of weighted average between different objective functions. And to first order, that's all there is, right?
Just to build on that, it often feels to me like when people talk about recovering structural parameters, I feel like they must have in the back of their mind partly something like what you're saying, which is that we're uncovering these parameters. We don't know yet what the decision will be, We might not know our loss function. We might not even know the decision we're going to make yet. But somehow the idea is that if we recover these parameters, it will be helpful for a variety of decisions and loss functions. I'm just sort of parsing a little bit back, I think, what you're saying. It feels like that argument shows up a lot. I'm just curious if that resonates with this framework, or if it feels like, don't be lazy, define your decision, define your loss function, you know.
I mean, sure. So I guess like, you know, the way I usually think about the structural is more about like invariance to relevant counterfactuals. What's the stuff that actually does stay the same when you do different things? But I guess people also make this argument that it might speak to all kinds of policy problems, for instance. And that's fine. There need not be obviously a trade-off, right? By, say, if I care about the effect of a, you can treat example, effect of a policy on both schooling outcomes and health outcomes of kids, it's not obvious that these two objectives are in any conflict to each other. If they are, then we have to make the trade-off somehow. And I would argue that, at least in the examples I've thought harder about, it's good to make the trade-off explicit rather than making some general claim about how knowing this answers all questions.
I was going to say, from Microsoft, we have this team in New York that does multi-world testing, which is a nice branding name for something that basically looks like randomization. But they actually have been pushing surprisingly hard the idea that you should do the opposite. You should randomize a lot, because you're going to have to make a lot of decisions. And you don't know what the decision you're going to have to make is. And so you should just be randomizing all over the place, and we can sort out the statistics later. And which is kind of interesting, right? Because you would think that if you could...
then you could make the claim that you should experiment a lot.
Yeah, exactly. I mean, this is... but not, you know, but for which... balance on which observables, for which problems I'm likely to have to solve in the future, right? It's kind of hard to know a priori what the right kind of non-random experimentation looks like.
Sure, but like, I don't know, if you want to make them look similar on age and on gender, right? In a large sample, there's no trade-off between the two. The only trade-off is in a finite sample. And sure, by making a choice there, you're making a choice, but by relying on a random number, you're also making a choice.
That's true. That's true. You're right, it's a choice.
But yeah.
Maybe a way to approach that formally would just, you could say that you have some space of decisions that you don't know yet.
Yeah.
And you want like a maximum or something. And I think maybe a prediction of something you get is something like, in the extreme limit, you're just trying to gather as much information as possible. Like your measure is just entropy and the number of bits of information you get. The other extreme is I have like a binary decision and I don't care at all about information because I know exactly what decision I'm going to make. So probably having uncertainty about your decision is going to translate to this, just gather information and figure out what to do with it later.
I would guess that the entropy argument is also going to rely on particular loss functions, but I haven't thought hard enough about it.
So isn't it maybe while the next speaker sets up?
I can ask it later.
Well, okay, so let's thank Max again.